Look at this solid circle. It seems perfectly straightforward, but mathematicians ask a surprisingly tricky question about it. What exactly is happening at its absolute outer edge? Think of it like buying a plot of land. When you purchase a yard, your property line has to end somewhere. But does your legal ownership include the heavy brick wall surrounding it, or do you only own the grass inside? If your ownership includes that solid physical wall, you have what mathematicians call a closed set. A set is closed when it contains its own boundary. But imagine a yard with no wall. Your property stretches right up to your neighbor's grass, stopping exactly at an invisible border. You own the space inside, but you do not own the border itself. In math, that is an open set. A set is just a mathematical collection of things, like a group of numbers or the points making up a shape. Slowing down, deciding whether a collection includes or excludes its outer limit changes how we calculate the nature of space. To see how this works without the distraction of grass and walls, let's look at a 1D number line. We'll focus on the space between 0 and 1. To make this a closed set, we highlight the space between 0 and 1 and place solid dots exactly on those end numbers. These dots represent our brick wall. If you stand directly on the number 1, you are on the furthest edge of this space. Because that edge is part of the collection, you are still inside the set. In an open set, we keep the space between the numbers, but use hollow circles at 0 and 1. This means the boundary numbers themselves are not part of the collection. This leads to a strange realization. If you remove the hard edge, every point left inside the set has something the closed set doesn't: infinite room to move. Standing at 0.9, you're inside. At 0.99, you're still inside. No matter how many nines you add, there is always a tiny, microscopic gap of space between you and that hollow boundary at 1. Because the boundary is missing, you can take smaller steps toward the edge forever without hitting a wall. Every point in an open set is surrounded by infinite wiggle room. Now, let's test a more extreme example. What if our set is just a single point, the number 7? This set has no inside or grass. It's just a boundary point all by itself. It fulfills the requirement to be a closed set. There are no hollow edges left out. This applies to all the whole numbers, stretching across the line. Even though there are infinitely many of these dots, they are just isolated points. They don't have that infinite wiggle room we found earlier. If you are at the number 6, any movement, no matter how small, takes you outside the set of integers. Because this collection is made of solid points and isn't missing any of its own boundaries, mathematicians classify the entire infinite collection of integers as a closed set. But look what happens if we fill in every possible fraction and decimal, creating a continuous, unbroken line of real numbers. This line goes on forever in both directions. Because it never ends, there are no boundary points left out in the cold. If a set isn't missing any boundaries, mathematics considers it a closed set. Since the real numbers have no boundaries to miss, they technically qualify as closed. At the same time, pick any point on this infinite line, and you'll find that infinite wiggle room on both sides. Every point is surrounded by other real numbers, the exact definition of an open set. This makes the real numbers a rare exception. Because they satisfy both definitions perfectly, they are a space that is both entirely open and entirely closed. Returning to our original shapes, we can see that these definitions are more than just technicalities. Instead, they are the vital tools we use to strictly define how points and spaces connect to one another. The next time you look at a shape or a boundary, ask yourself if the fence is included. That profound distinction provides the strict rules for the hidden geometry that literally makes up our physical world.